Welcome again to another module for the Big Data Analytics Summer School. In this module we will talk about random forests. So we will introduce random forests, show how they are used, show a brief example, and show how these ensemble classifiers use decision trees as they were explained in the module before. In the modules after that we then will discuss applications in detail ranging from space exploration to cancer research. So the name random forest and the originating paper for random forest came from Leo Breiman in 2001. Since then, you can see an explosion of usage of random forest. So today we have 30,000 citations and they are growing every single year. And what's interesting about that method is that it's really one of these methods which you can take off the shelf and most intuitively apply most of the time instantly without doing parameter optimization over a long period of time. So that's only one of the reasons why this method was so successful. Another one is that it is very transparent, can be easily expanded, and hence is used in a lot of different domains. So a quick history about random forests and decision trees. So there are some seminal papers. In '83, Leo Breiman presented CARDs. These are classification and regression trees. So these are the most fundamental decision tree classifiers, which were used a lot in the 80s and 90s. In '96, Breiman introduced bagging. Bagging takes random subsets or bootstrapped subsamples of the data and trains decision trees on these subsamples. And in the same year, Freund and Shapir introduced AdaBoost, which is again an ensemble classifier using trees. And for a lot of scenarios, they outperformed actually bagging, which Leo Breiman didn't like that much and came up with random forests a few years later, which in contrast to boosting don't overfit that easily and perform very well on a wide range of applications. So natural in science, nothing in science stands actually alone. So if we look at the history in between, there were actually several papers which proposed similar approaches. So one of the most important contributions were these randomized trees from Amit and Gieman, which nearly completely explain random forests years before Leo Breiman actually published his paper. Then parallel to that, Ho published decision forests, and also Dieterich published on random split selection. So these are also, that was a time where these ideas came up and fell on a fertile ground and significantly influenced machine learning and statistical research in the years after that. So a random forest is defined as follows. A random forest is a classifier consisting of a collection of tree-structured classifiers, H, which take x, which is the feature vector, as input based on some parameters at the split nodes theta k. And these theta k are IID distributed random vectors, and each tree casts a unit vote for the most popular class at input x. So that's the classical definition Breiman used. Nowadays we have variants on that in different aspects, which I will also introduce later. The common element in all of these procedures is that for the kth tree, a random vector theta k is generated, independent of the past random vectors theta 1 to theta k minus 1, but with the same distribution. And the tree is grown using the training set and theta k, resulting in a classifier h of x and theta k, where x is the input vector. So the point here is you end up with an ensemble of trees where every tree is grown on a slightly different subset with slightly different features, and that gives you diversity. And the power in these ensembles come from the diversity of the base classifiers. So in practice, the randomization in random forests comes in 2 dimensions. One are the samples, so every tree has different samples, and also in the features used. So here we see a very simple example. Again, we want to split a 2-dimensional feature space. And when we infer, when we train these trees, we would not check at every split node all possible features and choose the best one, as we would do if we train a normal tree, but we would randomly subselect only some features and choose the best feature of this subset. So, and the split criterion, the cost function we would use at these nodes, most of the time nowadays is information gain or entropy. Bryman proposed using the Gini index, which works quite well for unbalanced classes, and a very simple feature, as explained in the module about decision trees, would be the misclassification rate. So the second dimension of randomness in random forests is randomness on samples. So here's a simple example where we have a set of samples Z. So we have 6 samples, A to F. And then we draw bootstrap samples for every tree. So we draw the same number of samples with replacement. That means for every subset, C star 1 to C star T, we would have subsets where some samples are actually duplicated and some samples are missing. So for example, in the first one we have 2 Bs and 2 As, but we have no Fs and no Cs. So based on that, we then would train a tree based on all these subsets with randomness at the split nodes, as explained before. And the ensemble of all these trees is our random forest model. So the benefit of this approach is that it's not that prone to overfitting as single trees or boosting is. So every tree looks more or less or describes a subset in your feature space, and the combined ensemble gives you a powerful classifier which is very well suited for problems where you really need to generalize on new data. So if you now get a new sample, X, Y, and C in this case, you would throw these samples down every tree. So you would do classification of every sample as explained before. And for example, the first tree would classify X as 1, Y as 0, and the second tree would classify Y, contrary to the first tree, as 1, and the third one again would classify it as 0. And then at the end of the day, you take a majority vote over all trees, and that gives you the final classification. So that's the classification scheme described by Bryman in 2001. You can see what that procedure does not give you is a confidence. So you do not know based on that if it's very confident in classifying X as 1 or not. So one possibility to overcome that is, for example, to count the votes. So if the ratio of trees voting for 1 is just slightly higher than 0.5, the confidence would be low. Otherwise, if it's all trees agree on classifying X as 1, the confidence would be high. Another approach would be to actually average the posteriors of the trees. As explained in the decision tree module, if you learn a tree not to completion but stop early, you get a distribution of classes at every leaf node, and then you can use this distribution as posterior estimate, and then you can actually just average these histograms, which give you a nice posterior estimate for the whole ensemble. Another property of random forests which make it very suitable or useful for a lot of practical examples is that this procedure actually gives you an automatic estimate of the generalization error. So you would not have to split in training and test set, and if your samples are really IID distributed, but you could use the out-of-bag error. And the out-of-bag error comes from the fact that when you draw samples in a bootstrap procedure from your set of samples, you always have samples which are left over, which are not used. So we have here the same example as before, and for C1, that we draw a bootstrap sample from our 6 samples, have duplicated B and A, but we did not draw D and F. So the tree, the first tree, is learned only on the samples B, E, A, C, and not D and F. So for the first tree, D and F are actually test samples. They were never used for training, but could now be used to test how well the tree can classify D or F. So the same is true for all the other trees. So for every tree you have some samples which are actually left out during the training procedure. And if you have an ensemble of a few hundred trees, you can imagine that every sample is approximately 1/3 of the time left out of training and then can be used for estimating the generalization error. So it has to be noted here that this procedure only works if the samples are really independently distributed. In most vision scenarios, for example, you would classify, let's say, pixels, which are neighboring pixels and which are highly correlated. So if you use that for image pixels, this high correlation would give you an absolutely overestimation of the classifier, and you would be too positive because you have very similar samples in every single tree. So for some scenarios, like in computer vision, you would still want to have a nice split between training, validation, and testing set. But in a lot of other scenarios where in cancer research, for example, the samples are independent patients, the out-of-bag error is a very useful estimate, which comes for free when training a random forest. So here we see the development, the convergence of the out-of-bag error for an example. So here we have 2 classes again, and we learn 500 trees in total, as you can see on the x-axis on the right plot, and on the y-axis we have the out-of-bag error. So if you look at that in detail, you can see if you would only use one tree, your error would be quite high, in that case around 8%. And as soon as you start using more trees, your error goes down significantly, but only until a specific point. Approximately around 100 trees, the error converges, and regardless how many trees you add afterwards, your average error would not improve. So that actually shows this nice property that you can add as many trees as you want and you would not start overfitting. In practice, you would then cut the ensemble after 100 trees and use the random forest with 100 trees as your model for classification or prediction in the future. Another important property of random forests is intrinsic max margin property. So here at the top left, you have a very simple example. So we have 2 point clouds, a green one and a red one, and we want to classify these. So naturally, as you can see, there are tons of possibilities to split the feature space in both directions, to split up these 2 point clouds. But what you really would like to have is some ability, like in a support vector machine, to have some splits nicely in between these point clouds. So if you start classifying new samples, which are close to the clouds of the old samples, they would be nicely fall in this class. And the nice thing about randomization and random forests is if you in this case, randomly pick your feature and then optimize the split criterion, or even also randomize the splits which are chosen, you end up with a lot of different splits on every dimension, x and y. So that's something you can see on the top right. Let's see, tree number 43 would solve the problem by just splitting on the y-axis, quite close to the red cluster. On the other hand, tree 21 would split vertically to separate the problem. If you have now hundreds of these trees, every tree would split a little bit different, but on average, you would get class purity on one side, or in one area of your feature space, and also in the other extreme where you have a lot of the other samples, but in between it would be more or less washed out. So you can see this development on the bottom plot. So at the beginning is if you just have one tree, you have a binary partition of the feature space, and then if you add more trees, like 8 in the middle, or at the end 200 trees, you have this nice gradient from one class to the other class. So if you would get a sample exactly in between of your two training sets, it would be classified with very low confidence. So the entropy would be very high, whereas if the sample is close to the samples you saw before, you can actually get a classification with high confidence. So that's a very desired property which helps a lot for improving the generalization error. So this is the last example for this module. Here we can see how random forests perform on more complicated examples. So in the columns we have a 2-class problem at the beginning, then in the center a 4-class problem, and a noisy 4-class problem on the right. At the top you see the training input, that's where the random forest was trained on. And in the center you see the testing posteriors. So every coordinate in this image was classified by a random forest, and you end up with these nice spiral structures, which really nicely follow the classes, where you have large confidence, where you have training samples, and lower confidence between the two classes, even along the spiral arms. And the bottom plot would shows you the entropy, so the entropy between classes, and that could be used as a measure for confidence of the random forest ensemble. Thank you.